Welcome to the video instructions for the Revolution of the Moons of Jupiter lab. In this lab, you are going to weigh Jupiter. You will determine the mass of the planet Jupiter. And that cannot be done by merely going to the planet and, let's say, placing the planet on a scale. Here on the Earth, in a physics laboratory, typically the way you would weigh something, or in your kitchen even, is just to set the thing on a digital scale, let's say. We can't just go to Jupiter and set it on a digital scale. First of all, that kind of field trip is not really in the budget for our school. And also, if you think about it, imagine a life form on this planet like Big Bird. Big Bird would be standing with this orientation. And from Big Bird's perspective, that would look something like this. And in which case, wouldn't the scale just be upside down and it would just fall to the surface of the planet? So of course, that's silly. You cannot weigh a planet by setting it on top of a scale. So how are we going to do it? It'll have to be done indirectly. Also, there's some other challenges here. The atmosphere there, I forget if it's super hot or super cold, but the pressure is probably tremendous. It's a very inhospitable place for life, so Big Bird would end up looking something like that. Here are the four so-called Galilean moons of Jupiter, named after Galileo because, as I recall, he was the first to observe them or really study them in detail through a telescope. He didn't invent the telescope, but he was one of the early users of a telescope, and he improved on them significantly. This is an actual image taken through a telescope of Jupiter and its four moons. Surprisingly, it's not hard to see those moons. If you have a modest-sized amateur telescope, any night that Jupiter's up, you can see those moons, weather permitting. And of course, this is not an actual photograph. The moons, I don't think would ever be found simultaneously this clustered together next to Jupiter, but separately, each of these, well, yeah, even these are not actual images. This is an actual image of Jupiter. There's a mnemonic device worth remembering. The four names here appear in order: Io, Europa, Ganymede, and Callisto. I eat green carrots. That's not a true statement, but at least not for me, but that will help you remember the order of the planets, of the moons, in terms of their distance from Jupiter. So Io is the closest one, then Europa, followed by Ganymede, and the one farthest from Jupiter is Callisto, as you see here. Now, the moons, just like the planets going around the sun, the moons probably have elliptical orbits that are nearly circular. So throughout this lab, we are going to approximate the orbit of Callisto in particular as circular, despite the fact that it's really an ellipse, roughly. Here are some actual images taken from the Hubble. I think you can find more high-definition images taken by probes as they passed Jupiter and its moons. Remember, the Hubble telescope is in orbit around the Earth, so it's very close to the Earth. Any pictures that the Hubble takes are basically taken from Earth, but you can find better images taken by something that actually passed Jupiter. So those pictures would be much more close up than what you're looking at here. And here's a nice GIF of the moons orbiting Jupiter. I count 4, and you'll notice the one closest to Jupiter is moving the fastest through space. The one way out here has the lowest speed. Alternatively, you could say that the innermost moon has the shortest period. See how little time it takes the innermost moon to orbit Jupiter? So it's got a short period, whereas the one much further out has a much longer period of orbit. Again, here's some actual, well, this is a GIF, but it's a time lapse of the moons really orbiting Jupiter. And because Jupiter is so much more massive than the Earth, its gravity is quite a bit stronger. And so those moons whip around Jupiter in a matter of hours or days, unlike our moon, which takes a full month to orbit planet Earth. We don't really need this information for the lab, but I forget how many moons have now been counted. I think over 60. I'm not familiar with the actual definition of moon. Like, when is it just a rock versus something large enough to be called a moon? But there's a whole lot of satellites, natural satellites, orbiting Jupiter. And I believe only 4 can be seen from the Earth with the telescope. The rest of them are just too small. This guy's probably supposed to be Galileo, and he's letting one of his buddies look through his telescope. And this is an actual sketch made by Galileo as he observed on a nightly basis. He observed the moons moving around Jupiter. Actually, some of these pictures may have been drawn just hours apart. You can Google this and find tons of other scans of his handwritten notes on the web. Vocabulary. Depending on which class you take or which book you use, different letters will be used for these quantities. But instead of using capital T, let's go with lowercase p or just p for the period of the orbit. That's the amount of time it takes one of the moons to orbit Jupiter once. And like I said, we'll be looking specifically at Callisto. So P is for period. And then you could use D for diameter or even R for radius, but we will use the letter A. It's customary to use the letter A for the, oh, this is mislabeled. Hang on a second. Need to fix that. A is the letter typically used for the semi-major axis of an orbit. Remember, if the orbit were an ellipse, the longest distance that you could draw across the ellipse, that's called the major axis. Half of that is called the semi-major axis. And if your ellipse really is a circle, in other words, an ellipse with an eccentricity of 0, then the semi-major axis is the same thing as the radius. So rather than call this the radius with the letter R, we will use the letter A. That's going to show up in your lab instructions, the written instructions. Okay, well, hopefully at this point in the semester you've been exposed to Kepler's laws. Here's a famous portrait of Johannes Kepler. Now, this says Brohannes Kepler. That's a mistake. I'll have to fix that. And evidently, during this time period, the late 16th century, early 17th century, it was customary to wear an air filter around your neck. That was the fashion of the time. Maybe that was because Kepler was a big fan of Chinese food. You see he's got his chopsticks here, and I guess he was a messy eater, probably got a lot of food stuck in his beard. So this is like a big bib that he would wear around his neck. And Kepler was an assistant to an older, more famous astronomer named Tycho Brahe. Tycho Brahe, who put these slides together? So I'll have to fix both of these. He also wore an air filter, and it's not clear in this portrait, but he has a gold nose. I think he lost it in a duel over a woman. Somebody chopped his nose off. So because he was an aristocrat, he could afford a gold replacement. And, there's legends about how he had his own observatory on an island, and he would throw wild parties that involved a pet moose, and he would give the moose beer, and the moose would get drunk and rampage. These are all things I've heard about Tycho Brahe's life. Okay, so here are the real names. Tycho Brahe, Tycho Brahe, and Johannes Kepler. Lots of fun history between these two, but that's a topic for another time. Kepler is the one who made 3 revolutionary observations, no pun intended, in astronomy. The 3 laws. The first one is the one about how the planets move in elliptical orbits around the sun. Everybody else before that was obsessed with circular orbits. The second one is about equal areas and equal times. Basically, when a planet is closer to the sun is when it whips around faster, and then it slows down as it gets far from the sun. The third one is the one that concerns us. It compares the orbits of different planets, and he observed that the planets, well, this was fairly obvious before him, the planets that are farther out take longer to go around, but he actually went further and came up with a quantitative relationship. So let's look at these numbers here. Each of the planets has its period, its orbital period, listed not in seconds or hours or days, but Earth years. So of course it takes Earth 1 Earth year to go around the sun, but it takes Venus about 61% of a year. So when we say, or when I say 1 year right now, I'm referring to an Earth year. So those periods are listed, and then the size of the orbit is listed. There's that letter A, and it's given in astronomical units. I've got some graphics in a moment, but 1 astronomical unit is how far Earth is from the sun. So let's continue with Venus. Evidently here, Venus is 72% as far from the sun as is Earth. So if you have a column of all the periods of the planets in Earth years and all of their semi-major axes, basically the radii of their orbits, in AU. There's a relationship that's not immediately obvious. I mean, what we can see just by glancing here is that as the size of the orbit increases, so does the orbital period, which makes sense. The farther out the planet, the longer it takes to go around the sun. But, and I don't know how Kepler discovered this because he did not have a handheld calculator. Even paper was expensive back then, so did he spend hundreds of hours just doing arithmetic by hand to discover this? They didn't use graphs the way we use them now, so I really do not know how he stumbled across this. But if you take all of these numbers, the periods, and you square them, in other words, multiply by themselves, so 0.24 times 0.24, that would give you this number. 0.61 times 0.61 would give you 0.37. Square all the periods, and then go over to this column, which gives you the size of the axes. Take each of those numbers and cube it. So Venus, for instance, 0.72 times 0.72 times 0.72 would give you 0.37. And voila, the square of the period is the same number as the cube of the semi-major axis for every one of these planets. Of course, the agreement is not exact. Surprisingly, it's nearly exact for every one of these planets. That cannot be a coincidence, right? If it were true for one or two of the planets, you might conclude it's just happenstance. But the fact that this pattern holds for every planet suggests that there's some physical law at work, and Kepler was not able to explain that. He didn't have a physical explanation for why the square of the period should equal the cube of the orbit. I wouldn't really call him a physicist. He was an astronomer, a mathematician, among other things, but still groundbreaking to have discovered this pattern. And I'll point out that in his time, they were not familiar with these last three planets. Their existence had not been discovered yet. But all of these first planets, including Earth, can be seen in the night sky. I should say with the exception of Earth, because we're standing on Earth. But those other 5 planets can all be seen with the naked eye. I myself was surprised to realize that you can see Saturn easily with the naked eye. You don't see the rings without a telescope, but it's a blue dot in the sky. So here is a way of stating that result mathematically, just like you'd expect. Take the period, square it, take the semi-major axis and cube it, and those two numbers are the same. That's what the equality means. But it's very important to keep in mind, you can only write Kepler's third law in this form if you use the following units. You must be talking about the period in Earth years, and you must be expressing the semi-major axis in astronomical units. If you were to measure the period in days, let's say, and the size of the orbit in miles, then these two numbers would not be the same at all. So the equality depends on using those special units. And just to remind you, the AU, the astronomical unit, is the distance from the center of the sun to the center of the Earth. And you know what? I just realized something. Because when I see AU, I think of Australia. And believe it or not, the expedition in the 1760s, I believe it was, there was a guy named Captain Cook on a ship with a bunch of sailors, and they had instructions from the King of England at the time to do a number of things on this expedition. One of their directives was to stop off on the islands of Tahiti and make some astronomical observations. Venus crossed in front of the sun, and they had to make some recordings of measurements that they made. And that data was used to calculate how far the sun was from the Earth, believe it or not. And on that same expedition, I believe they discovered Australia. So that's kind of weird, because the distance to the sun, which was first determined because of that expedition, is called the astronomical unit. And on that same expedition, they discovered Australia. I wonder if anybody else has ever noticed that. Okay, moving on. So distance from sun to Earth, that's the astronomical unit. Now, if you express that distance in kilometers, you would say the sun is something like 150 million kilometers away. So the answer to the question, how far away is the sun, if you give your answer in kilometers, would be 150 million. The answer to that same question, if the units used are astronomical units, how far away is the sun? The answer is 1. 1 what? Well, 1 astronomical unit. How far is Mars from the sun? 1.5 astronomical units. Here's a really nice, really nice GIF I found on the web. This is called an orrery, O-R-R-E-R-Y, orrery. It's they used to have mechanical ones where you turn a crank and like little brass spheres representing the planets would orbit each other or orbit the sun. And it simultaneously shows you the moon going through its phases. You can see planet Earth here with its own moon orbiting it, the inner planets. This is probably Jupiter and Saturn with their outer planets, or outer moons, excuse me. Yeah, I'm throwing this up because you can see Kepler's third law at play here. The farther you go from the sun, the longer it takes each of those planets to orbit the sun. But it was discovered after Kepler that that relationship, the square of the period being equal to the cube of the size of the orbit, it doesn't just work for planets going around the sun. You can also apply it to these smaller systems of moons orbiting Jupiter. So if you look at the period of the moons orbiting Jupiter, the same law will apply. So we're looking at a close-up now of the Galilean moons orbiting Jupiter. And we will be applying Kepler's third law not to the planets orbiting the sun, but to the Galilean moons orbiting Jupiter. But we need a slight modification. So I mentioned that Kepler was not able to explain why this relationship was true. Newton came along in the 1600s, developed calculus, developed the branch of physics we call mechanics, and had a very precise explanation. He was able to calculate the motion of the planets using something that we now call Newton's second law, Newton's law of gravity. You've seen some of this. So an updated version of the formula accounts for what's at the center of your system of satellites. In Kepler's case, it was the sun that was at the center, but now we're talking about Jupiter at the center. So you have to put this term out front, 1 over m. So this is the mass of the very massive body at the center of your system of orbiting satellites. And again, this formula only works if you use some very special units. You have to continue measuring the period in Earth years. You have to continue measuring the semi-major axis in AU, and the mass can't be measured in any arbitrary units. It can't just be in kilograms. It has to be in multiples of our sun's mass, the sun's mass. We call those solar masses or solar mass units. So the next thing we can do is rearrange this equation. Let's solve it for m, because after all, that's what we're trying to do here. We are going to weigh Jupiter indirectly by observing the motion of its satellites, how quickly they whip around based on how far they are from Jupiter. We can determine the mass of Jupiter. It should make some sense intuitively because, again, our moon takes an entire month to orbit the Earth. And yet some of these moons of Jupiter whip around in a matter of hours. That's because Jupiter's gravity is so much stronger. Why? Because Jupiter is so much more massive. Solve for m and you get this. So this is presented in the written handout for this lab. You'll be provided with written instructions, very detailed instructions, and this formula is in there. You will be determining the size of the orbit, A, and the period of the orbit, P, for Callisto, the outermost moon of Jupiter. Once you've determined those numbers, you can plug them into this formula and find the mass of Jupiter in terms of the sun's mass. It'll be in solar mass units. So when we look at this picture of the moons orbiting Jupiter, m is the mass at the center. It's the mass of Jupiter. We're no longer talking about the planets orbiting the sun. Okay, there's a number of mathematical details we have to discuss here. This is, of course, not to scale at all, but here's a view from above of our solar system highlighting Earth orbiting the sun, and then much farther out, again, this is not to scale, Jupiter is also orbiting the sun while its moon Callisto orbits Jupiter. There's a bunch of other moons, but I've only shown the outermost moon, Callisto. And I'm using these letters to be consistent with a diagram presented in the lab, but also to be consistent with a lab we did previously. Those of you in my astronomy lab class, we measured the angular size of something like a door at the end of a hallway. and used that to estimate the actual size in meters of the doorway. And I think we actually used the letter H in that case for the height. But we could use D as well. So R is the distance from planet Earth where supposedly you would, or presumably you would be standing and looking through a telescope at Jupiter. So it's the distance from your eyeball, basically, to Jupiter. But we will be looking at the distance between Jupiter and Callisto. So if you pointed one finger, like the finger of your right hand at Callisto and the finger of your left hand at Jupiter, the angle between your arms is the angle that I will call theta. This is called the angular distance between Jupiter and its moon. And what we'd like to know is the actual physical distance in meters, miles, astronomical units, etc., between them. So we will be converting from the angular distance, which is what you would see in your field of view, and the actual physical distance. And in order to do that, we have to know the distance from Earth to Jupiter. So knowing R and knowing theta, we can find D. However, there's a difficulty here, which is the fact that all the time these two planets are moving. They're moving along their orbits around the sun. So at some later time, you see now R is greater than it was. Jupiter is now farther from the Earth than it was previously. And because Callisto is always moving around Jupiter, the angle theta has changed. So theta is always changing, and R is always changing. And that means that this distance between Jupiter and Callisto is also changing. Now, there's a little subtlety here. If you'll note here that D is not really the distance from Jupiter to Callisto. This would be the distance between those two. D is like the arc length. So if you imagine taking this distance R and just sweeping it over to the line of sight from Earth and Jupiter, D is that perpendicular distance. That's really what we will be putting into a spreadsheet. Now here, just a moment later, Callisto has made its way to the other side of Jupiter. And we will be considering a distance like this to be a negative number. Let me elaborate. Here is Jupiter. Let's imagine Jupiter as at the origin of a real number line. Remember the number line, if this is the origin or 0, positive numbers are over here, negative numbers are over here. So we will be assigning a coordinate to Callisto. And Callisto is really not this big compared to Jupiter, so this is not to scale. But when Callisto is over here, its coordinate is some positive number. If I plopped it over here, it would be a greater positive number. When Callisto is on the left side of Jupiter in your field of view, because in case I haven't mentioned, we will be using Stellarium to make these observations. When Callisto is on the other side of Jupiter, its coordinate will be considered negative. Do not forget the minus signs. You're going to create a lot of extra work for yourself if you forget to be observant of minus signs in this lab. Now, conceptually, this is challenging for a lot of people here. Okay, so up in the corner, I've got a picture of Jupiter with Callisto orbiting, and I'll be updating that picture. And right now, since Callisto is just to the right of Jupiter's, its coordinate would be a positive number, but not a very large number because it's not far from Jupiter. So this vertical axis will be used to represent the distance, or I should say the x-coordinate of Jupiter. So moving in this direction up on the page corresponds to Jupiter moving to the right, farther away from Jupiter. On the other hand, if we go downwards on the graph, that represents motion of Callisto to the left on the other side of Jupiter. So what I'm going to do is just keep updating the picture here. You have to imagine Callisto orbiting Jupiter, and I will be making daily observations. And really, you should just pretend this is some other moon, not Callisto. It's just some arbitrary satellite of Jupiter, because the numbers I'm presenting right here as an example do not match the actual data for Callisto. Okay, so let's advance one day and observe where Jupiter is. See how it's moved farther from Jupiter, but it's still on the positive side. So motion to the right along this axis, this is the time axis. So this corresponds to moving one day into the future, and I've put a marker up here to indicate that the moon is now farther from Jupiter and it's on the positive side. So each of these markers indicate where the moon was on a particular day and where in space. One day later, notice what happened here. The moon presumably would have continued to move to the right, and then it would have stopped, turned around, and now it's back closer to Jupiter. So what happened between this slide and this slide was the moon went all the way out to its farthest point and then retreated to here. One day later, if we look at the graph, we expect it to be, well, we're back at the origin, meaning it should be right on top of Jupiter. And there it is, maybe a little bit to the left. And you'll notice that the moon is in front of Jupiter. If this moon is really orbiting Jupiter, then eventually it should go behind Jupiter. So I'll try to point that out when we get there. What do we expect one day later? Well, that's when the x-coordinate is very negative. So the moon should be over here somewhere, far from Jupiter in the negative direction. And there it is. One day later, it will have already reached its leftmost point and come back a little bit. So we shouldn't see too much of a change. See that? So from here, whoops, from here to here, it finished its motion to the left and then came back. Now it's past Jupiter again, and it's on the right side. Now, this picture is a little misleading. This moon would actually be behind Jupiter at this point because previously it was in front. It's going to have to go around behind before it comes back in front. Okay, one day later, it's almost as far to the right as it's going to get. I think you get the picture at this point. Let me just continue these one day at a time. This next one we can see the x-coordinate of the moon would be basically 0, so it's either right in front or right in back. And I think for this pass we would be behind Jupiter. Yeah. So when you do this lab in Stellarium, there may be days when you do not see Callisto because it's behind Jupiter, and that's okay. Now, how do we use this graph to extract the information that we want? First of all, I should point out, you will be making this graph in Microsoft Excel. And when you begin making it, you're not going to see the plot. You'll be collecting the points first and asking Excel to fit the curve as best as possible. Actually, we don't even do that. I think we just connect the dots. Well, I'll come back to that. But once you've constructed your plot, you can visualize the necessary data from the graph. So if you think about it, let's traverse the curve here. Suppose this is Callisto. Again, the number that I'm putting up here is just for practice. It doesn't match the data you're going to have. But this is when Callisto is basically right on top of Jupiter. It's moving to the right. This is as far as it gets from Jupiter. And then it comes back. Let's say it passes behind Jupiter. And then goes as far to the left as it's going to go. Then it comes back. Now it's in front of Jupiter. Now it's all the way to the right. You get the idea. So farthest to the right, farthest to the left, and then farthest to the right again. That means this time duration right here is how long it takes to return to where it was previously. So I've picked an arbitrary starting point in the orbit. That's where the moon is farthest to the right. And I've waited until it gets back there. That's what we call the period. That's the amount of time it takes to, to trace through your steps once. So if we could figure out what this time is in days, we could then convert it to seconds or years as needed. We would know the period of the orbit. That's what we're doing. So you're going to be collecting data on a daily basis in Stellarium and then plotting it in Microsoft Excel and extracting the period of the orbit from this curve. And by the way, if you've taken pre-calculus or trigonometry, you've seen sine functions, sine and cosine. They both have this shape. So we really have something that closely approximates a sinusoid, and we call this the period of that sinusoid. Well, my time scale down here is in days. So I can draw some vertical lines, and you may actually want to do this. You could extract this information from within Excel, but the people who get the best results often are the ones who print out the graph and use a ruler to complete these steps. So I encourage you to do that. If you've printed out the graph, you can draw a vertical line through two subsequent peaks in the graph. And then you can estimate There is some estimation required here. In fact, what we're doing is interpolating. So this notch represents 1 day into observation. This notch is 2 days, and I can see that this vertical line falls at a place a little less than halfway from 1 day to 2 days. Now, halfway would be 1.5 days, 1.5 days. To me, this looks like, if I had to guess, 3/10 of the way, maybe even 4/10, but I'm going to go with 3/10. Over here, this line is almost halfway between this notch, and if you count 1, 2, 3, 4, 5, 6, this is day 7, this is day 8, so I just estimated day 7.4 is the peak here. The time that we're interested in is how much time passes between those 2 points in time. So all we have to do is subtract. You'll have to make two measurements there of time and then subtract. So the later day minus the earlier day would give me a period of 6.1 days. Remember, I made these numbers up. That's not the actual period of Callisto's orbit. Great, we're partway done. We've already got one of the two numbers that we need. Now, how are we supposed to get the semi-major axis from this graph? Remember, the vertical coordinate here tells us the location in space of Callisto with respect to Jupiter, or of this moon we're talking about. Sometimes the moon is to the right, sometimes it's to the left. Now, if you think about it, its greatest distance from Jupiter would in fact be the semi-major axis, loosely speaking, because remember, this might be an ellipse, and that complicates things slightly, but we're just pretending it's a circle, and we're pretending that we're looking at that orbit edge on. That's another source of complication. You know, what if our view is actually slightly above the plane of the orbit? Let's not worry about that for now. So we need to figure out what the maximum absolute value of the x-coordinate is. And that's really what you would call the amplitude of this curve. So for a sinusoid, the amplitude is just the highest point on the curve with respect to the horizontal axis. That's it. Now, in Excel, you'll actually have, I expect you to have a scale here. So you could do something like draw a horizontal line if you've printed it out and use the same process of interpolation to estimate what this height is. A better way to do it probably would be in Excel, you can hover, and I'll show you this later, you can hover your mouse over the peak and it will actually give you the coordinates, and you would take the second coordinate. You know how usually you in an ordered pair you list the horizontal coordinate first and then the vertical coordinate. Now if you had printed this out, a better way, a more accurate way of determining the amplitude, which in this case is the semi-major axis A. So it's kind of like the letter A is doing double duty right now, A for amplitude, but also A for semi-major axis. You could print it out and draw this horizontal line through the various peaks and draw the one down here as well. And then you can see that this distance would be twice the amplitude. So you could just measure this distance in astronomical units, of course, and then divide by 2. Don't forget to divide by 2. It's up to you how you want to do that. Just try to get a precise number. Okay, and I will be demonstrating a lot of this stuff to you, but here's another mathematical detail that you need. This is the formula that you saw earlier in the semester for converting from angular size to actual physical distance. Like I said, previously I think I used an H for the height of a door, for instance, but you used the finger rule method. You used your pinky finger maybe to estimate the angular size of something in your field of view. Then you multiply by how far away that object was to get the actual size in inches, let's say, of that thing, whether it was the height of a door or the height of a Coke can. This is the relation that we're using, and of course that's why we did it earlier in the semester, so that you would be familiar with it when we got to this more interesting topic. But now, instead of talking about the height of a door over here or the height of a Coke can, we're actually talking about the distance between Jupiter and its moon Callisto. And this angular size will be measured in stellarium, so we're not going to be estimating it. You could go out at night, I suppose. Well, you can't see Jupiter and its moons with the naked eye, but for something larger you could use the finger rule. And of course we also need to know the distance to Jupiter. We will be relying on stellarium to give us that information. Do you remember that this equation only works if you plug in the number theta in radians. You have to be measuring angles in radians for this to work. But Stellarium is going to report the angle in degrees. So you don't need to know this, but here's the conversion factor. Pi radians is the same as 180. If you do this division in a calculator, oh, I didn't actually put that in. It's something like 0.0714. I forget the number exactly, but that was in your previous lab. And you'll be doing that in Excel. So let's also review here. 1 degree is too large of an angle to describe most things in astronomy. Even the moon is smaller than 1 degree in your field of view. So we take a degree here. Here they're showing us 30 degrees. This 30 degrees sector, let's see. I guess this would be 2.5 degrees, 5, 7.5, 10, whatever. Take one degree. This is 30, right? Take one of those 30 degrees, and they've had to exaggerate the angle so that you can actually see it. I mean, obviously this is not 1 degree. This is closer to like 40 degrees. But if you could take that 1 degree and then chop it up into 60 smaller angles, 1/60th of a degree is called 1 minute. The word minute is like minute or small. So a 60th of a degree is called a minute. Technically, it's a minute of arc, not a minute of time. You're used to hearing about minutes of time. And that's a fairly small angle, right? Remember that the moon is about half of a degree in your field of view. It's about half the width of your pinky at arm's length. Well, half of 60 minutes per degree would be about 30 minutes of arc. So you could say that the moon is half a degree across or 30 minutes of arc across. One step further would be to take each of those minutes. A minute is already pretty small. In fact, I think a minute is like the thickness of your fingernail at arm's length. That's small. It's like the thickness of a credit card. Take that minute and chop it up into 60 even smaller angles. Those are called seconds. It works the same way as the way we divide up the hour into minutes and then seconds. We're using this number 60. As far as writing it down, here's some abbreviations. 1 apostrophe, that means 1 minute. It's the same as 60 seconds. So 2 apostrophes is seconds, 1 apostrophe. How come we don't say apostrophe? That's the way it looks to me. Apostrophe looks like apostrophe. Now, what have I done here? Well, 1 degree has 60 minutes, or is the same as 60 minutes, but each minute is the same as 60 seconds of arc. So 60 times 60 tells us that 1 degree has 3,600 or 3,600 seconds of arc. We're going to use that because Stellarium is going to, the tool that we're using in Stellarium will give you the angular size in degrees, minutes, seconds. Here's an example of how to convert from DMS, that's degrees, minutes, seconds, to so-called decimal degrees. Because in the spreadsheet, we need to be working with our angle in decimal degrees. So suppose you're looking at something in the sky whose angular size is 2 degrees plus 24 minutes plus 56 seconds. This is a very common way of specifying an angle in astronomy. For some purposes, it's more convenient than working with the decimal. It's really straightforward to convert. All you have to remember is that a minute of arc is 1/60th of a degree. And a second of arc is 1/60th of 1/60th of a degree. In other words, 1/3600th of a degree. So this angle in DMS, degrees, minutes, seconds, is really 2 degrees plus 24/60ths of a degree plus 56 3600ths of a degree. And then you can just plug all this into the calculator. Obviously, the degrees are just understood, but if you get rid of the degree symbol here, everything else can just be punched into a calculator. Now, you will be measuring the distance from Callisto to Jupiter a bunch of times, and you don't want to do this by hand every time. That's why you're going to use a spreadsheet. So it will be a little pesky for you to learn how to use Excel if you've never used a spreadsheet the way we're using it here. But once you get the hang of it, you'll see how useful it is. It saves you a ton of time. This is the number that would come out of the calculator. So again, They both have the repeal. When I write it this way, it's obvious to me that I'm talking about less than 2.5 degrees, because 2.5 will be 2.5. And I've got, let's see, 5 significant digits here. I guess over here, I've also got 5 significant digits. It's just written using a different number system. Okay, that's how to convert from DMS to decimal degrees. And you will be instructing Excel to do this with all of your measurements. Okay. And, well, I guess I'll go over this now. Ultimately, remember the formula for the mass in terms of the period of Callisto and the semi-major axis? That number is going to come out in solar mass units. Remember that. I'll do an example for Saturn. This symbol is used in astronomy to signify the mass of the sun. This is the symbol for the sun. So I looked this up. Saturn, we're talking about Jupiter, of course, but Saturn has a mass quite a bit smaller than the mass of the sun. So we're in the tenths, tenths, hundredths, thousandths. This is in the 10,000th place, 286 10,000ths of the mass of the sun. So that's a really small number. Saturn is enormous. It's more massive than the Earth, but the sun is just unimaginably large. What if we would like to state the mass of Saturn in kilograms? That would be a big number, because a liter of water has a mass of 1 kilogram. So the mass of Saturn in kilograms has got to be a huge number. Let's convert this mass expressed in solar mass units into a mass in kilograms. Here's how you would do that. You will be doing this for this lab. We'd like to cancel solar mass units and have kilograms come out. So here's my conversion factor. I know that 1 solar mass unit, well, that's just 1 times the mass of the sun. This is the sun's mass in kilograms. So by setting up the ratio in this way, we see that the solar mass units cancel, and what comes out is kilograms. And then you would just multiply this number by this number in your calculadora, and out comes the mass of the sun, the mass of Saturn in kilograms. And it is indeed a ginormous number. Not as ginormous as the sun's mass, but much bigger than the mass of anything that you're ever going to pick up, that's for sure. Here I am in Stellarium. I'll walk you through some of the procedure involved in this lab, but you really do need to read the instructions. That's where you should go for all the information about what to do in this lab. Don't just rely on these video instructions. Think of this as a supplement. The first thing you need to do in Stellarium is activate a plugin tool that we need. I'll show you that. I think it's in configuration window. Yes, we go over here to plugins, and we need, is it compass marks? No, I thought it was, here we go, angle measure. Go down to this button, or this box to check, load at startup, because by default it does not load. Once you have checked that, you can close out of here, and you actually need to shut down the program or restart the program. So you can do that with Alt F4 or just hit the X. So I'm going to close out this program and restart. Once I've done that, we should find that the angle tool is accessible, or the angle measure tool is accessible down here at the bottom in the toolbar. So here I am back in Stellarium after restarting. I go down to the bottom, and there it is, the angle measure tool. Click on that. Did I click on it? Okay, and now let me get rid of the sky. So I will hit A for atmosphere. Okay, what's the angular distance from Jupiter over here to Antares? So if I click, do I have to click and drag? Yeah, click and drag from one to the other. And in the lab, you're going to try to be as precise as possible. Notice how the angular distance between these two is given in degrees, minutes, seconds. And the seconds are given with 4 digits. So they give you the seconds out to the hundredths place. Now, I don't think you really need to, you don't actually need to keep all these digits, because there's some other larger sources of error in this lab. I should have a note in the written instructions about how many digits are worth keeping, but that's something to bear in mind. Now, to actually make our observations, remember, sorry, I'm having trouble with the mouse here. I'm trying to zoom out. Let's get rid of the ground. That's just in the way. I don't want to see these cardinal points. So the letter Q will get rid of those. And we're not interested in this angular size. We want to know the distance between Jupiter and one of its moons. So if I click on Jupiter, and for some reason Stellarium is giving me trouble here. Okay, rookie mistake. The source of the trouble there was I had to turn off the angle measure tool. So if you just want to click on things normally, you got to turn that tool off. Okay, I've clicked on Jupiter. I can hit the space bar to center, and now I'm going to zoom in. You can use the scroll wheel on the mouse. I like to use Control and the up and down arrow. So if I hold down Control and then I start tapping the up arrow, I can zoom in on Jupiter. And there are the moons. Now I'd like them to look more horizontal in my field of view. So if I go down here, I can change the camera mount to an equatorial mount, which is more natural. Great. Now, you probably want to hit spacebar a couple times to make sure that we're tracking Jupiter. Otherwise, it's just going to drift out of the field of view. Okay, now where's Callisto? There it is. We can see that there are other moons closer. And it's worth pointing out here that if I keep Jupiter centered, whoops, not Callisto, Jupiter. I'm going to speed up time a bit. So I'm going to hold down Shift and tap L a few times. That's a little too fast. Okay, that's good. It's kind of fun to watch the regular motion of the moons around Jupiter. It's like clockwork. They just keep going and going, not for hours, days, or even years. They've been doing this, presumably, for millions, hundreds of millions, billions of years. Those moons have been at it for billions of years with extremely regular motion. And so Galileo got to thinking, well, if they're that regular, if they really are moving like clockwork, then perhaps they actually could be used as a clock. So I'm going to interject a quick historical footnote. This is something I was kind of thrilled to learn about. Back before modern instruments for cartography or navigation, people would sail around the world, mapping out the New World, and in order to determine your latitude and longitude, latitude's pretty easy. You can use the stars to find your latitude very easily. But longitude requires having an accurate timepiece. So you needed a clock that you could take with you on your ship, set sail from, these particular people that I'm talking about came from Europe, set sail with your clock and have it still keep time accurately months later. And clocks like that used to not exist. So what Galileo suggested was making calculations about the positions of the moon relative to Jupiter at various times. And he suggested that you could create a table or tables of where the moon should be, like let's say on the hour, every day for the next several months. And so you could take those charts with you. And I assume those would be very expensive because it would be very laborious to produce charts like that, especially back then without calculators or computers or spreadsheets. You could take those charts with you, and then if you land on some island in the middle of the Atlantic Ocean, you could set up a telescope, because they did have telescopes, set up a telescope at night, observe the positions of the moons, and compare with your chart. And because you know where the moons should be at all times, because they act like the hands of a clock, you could then infer what time it was. And from that, you could determine your longitude. So, of course, I've left out the details. But from what I've read, this was actually done for a period of time. This was like the go-to method for some navigators or some intrepid, adventurous travelers who were mapping out coastlines. So you can Google that if you're interested. But the system of Galilean moons was actually regarded as a very accurate clock for a period of time in our history. Okay. Come back here. How do I stop this? K. Remember, the letter K will stop time. Okay, the first thing you want to do is just pick an arbitrary day and time. do not pick the same day and time as a friend of yours in the class. Everybody needs to do this lab themselves. I will be looking for copied data. So if you have the same day and start time as somebody else, or the same data, you're not going to get credit for the lab. So I would just fast forward in time as I've done, pick some arbitrary day and time. And down here, I can see that the date is February 26th of 2021. And I've got the time and my time zone. Remember, UTC is Universal Time Coordinate. That's the time in Greenwich, England. So UTC -7, that's what we use here in California during daylight saving time. So that information needs to be put in your spreadsheet. So I'm going to pause, pull up the template spreadsheet, which you will be provided with, and then we'll start filling out that spreadsheet. Okay, here I am in Windows 10 with the fancy dual pane mode here. Starting date. I'm going to enter that right here. So what did I say? February 26th, 2021. If I do this 2-26, or I should say /2021, I think Excel will be smart and know that I'm talking about a date. Okay, it didn't convert that yet, but if I do this, because I don't want to actually enter all these dates by hand, that's annoying. What I can do is say equals, and then click on the previous cell, and plus, so that's shift plus sign plus 1. I'm telling Excel, hey, take the previous cell and add 1 to that, and I'm hoping that Excel will be smart enough to recognize that I'm really telling it to take a date and add 1 day. If I hit enter, yeah, it figured it out. It knew I was referring to dates. Now, check this out. There's a couple ways to do this. If you hover over the lower right corner, see how these the white cross turned into a black cross? You're now ready to click and drag. So I can click, hold down, and drag all the way down, and it's going to repeat that for 28 days. You could also just double click. That would work as well. So let me undo, Control Z, undo. Let me try it the other way. I'll just double click in the lower right corner. That's another way to do it. So it just created a column of days, or dates, 28 days. It's spanning a range of 28 days. Your starting date will, of course, be different from mine. You can go back in time 1,000 years if you want. It doesn't matter. Just don't pick the same date as a friend in the class. And then starting time, begin time here. Okay, this is difficult because I've got okay, I'm going to write down the time 6:22:38, and I will include the time zone. This is a good way to record that information. This is how I would like to see it in your spreadsheet. So not only do I know the date on which you started your observations, I also know the starting time. That way, if I feel like it, I can go into Stellarium and just check your data here. See how I've given the time, and I've indicated my time zone, UTC -7. Okay, well, remember in the PowerPoint spreadsheet, that little diagram of Jupiter orbiting the sun with Earth orbiting the sun, and I labeled R, theta, and D. So Jupiter distance, that's really the distance from Earth to Jupiter, which I was calling R in the slideshow. That information is given here in Stellarium. See, there's a ton of data that we don't actually need. Down here towards the bottom somewhere, here it is, distance. They actually give you two distances, distance from the sun and then just distance. It's understood that that distance is the distance from the observation point, which is planet Earth. Now let's not worry about where on planet Earth, because the diameter of the Earth is nothing compared to the distance to Jupiter. So that's really not going to matter one way or the other. And they give us that distance in millions of kilometers, but also in AU. Let's go with AU. Make sure you write down the distance in AU. And you'll notice that in Excel, I've actually written that. It's Jupiter distance in AU. Okay, so maybe the first thing you should do, it is the first column after all, is record that number, 5.981. And that distance is going to change from one day to the next because Earth and Jupiter are both orbiting the sun, and so their separation is constantly changing. Okay, so we're making progress already. Now, remember in the slideshow, I used the letter X for the coordinate of Callisto with respect to Jupiter. So let me see if I can center this Jovian system. Okay, so we need the distance between Callisto and Jupiter. And I have to recognize that even though it's tilted a little bit, Callisto is off to the left of Jupiter. Maybe I should fix the camera mount again. Okay, it's already set to equatorial. It's even worse like this. Either way you look at it though, Callisto's on the left, is it not? I almost said it's on the left, right? But that's confusing because the word right is in there, is in that sentence. So let me go back to the angle tool and I will click and drag. Now if you zoom in a little bit, it's difficult for me to do that in the split screen mode, but try to zoom in and fill up the screen, or mostly fill up the screen with the separation between the two, because then your results will come out more accurately. I'm going to click in the center of Callisto and drag to the center of Jupiter. Again, yours will be larger so you can be more precise. And it's tough to read against all this background information here, but I see, can I right click? No, that didn't work. I just wanted to get rid of that pesky information. Okay, that looks to me like 0 degrees, 6 minutes, and 2.93 seconds. You should find that the number of minutes is always 0. And that's because even though we've zoomed in here, you know, if you're actually on planet Earth, all of that just looks like one dot. So the angular size is very small. It's always going to be less than 1 degree. So you'll notice in the spreadsheet, I did not even include a column for the number of degrees because it's always 0. But as far as the minutes go, 6 minutes. And then for seconds for now, I'm going to keep all the digits, 2.93. I probably have a statement in the instructions about how many digits you need to keep to save yourself some time. And that's it. I've just completed my observations for 1 day of the 28 days of observations. So it's a little tedious. You have to do this 28 times, but once you get the hang of it, it should go quickly. Now, as far as advancing 1 day forward, see, I've already forgotten the keyboard shortcuts, but I believe it's the plus and minus sign. So I'm going to look at the date down here. What happens if I hit the plus sign? Oops, I'm still in Excel. Okay, so I have to click in the other window. If I hit the plus sign, aha, now it's February 27th. Now you want to make sure that it's the same day. Excuse me, the same time, sorry. So make sure that time is stopped, because you really do want your measurements to be 1 day apart, not 1 day plus or minus half a minute or a couple minutes. So make sure that the time is stopped. You can do that with the letter K. You don't want to see the seconds ticking forward. And then use plus and minus to go ahead 1 day at a time. And you can see how everything shifted, right? So let me, yeah, this split screen mode is making it difficult for me. Okay, let's see if the angular distance between them has changed. Definitely. It was 6 minutes and some change, now it's 4 minutes. So on day 2, and before I forget, well, okay, I'll put the minutes in first. 4 minutes, 2.54 seconds. But really, you should probably put the Jupiter distances in first before you forget. So you're only going to see that information about Jupiter if you click on Jupiter. So I have to deactivate the tool. Yeah, now you can see why this is a little pesky. Click on Jupiter. Make sure you get the distance first, not distance to Sun. So 5.974, it did change a little bit. 5.974. All right, I have 2 days of data now. Just rinse and repeat. Advance 1 day by hitting the plus sign. Click on Jupiter, get the distance, then turn on the angle measure tool. Click and stretch between Callisto and Jupiter, get the minutes and the seconds. Aha, I'm so glad I made this mistake, because otherwise you would have been making it. Don't forget, we need minus signs. Callisto's on the left side, so both of these need to be negative, both of them. Yeah, it's going to cost you a lot of extra work if you forget the minus sign, because if you take all this data and you don't include the minus signs, then when you look back at it, you're not going to remember, you know, when was Callisto on the right versus the left. So make sure to include the minus signs, and they both need to be negative if Callisto is on the left side. Once Callisto jumps over to the right side, you can switch back to positive numbers. Now, if there's a day where Callisto is blocked by Jupiter, let's say on day 7, you can't even see it, go ahead and write the distance, I suppose, but you could just leave these blank. Don't even put a number there. If you want, you could put 0, but that's kind of misleading because just because you can't see Callisto doesn't mean that it's actually centered on the origin, which is the center of Jupiter. So it might be better just to leave it blank. Your graph will still come out nice. Now, if you skip that day altogether and you actually put in the numbers for the next day, that will screw up your graph. So make sure to leave that row blank or enter 0. I would just leave it blank. Okay, I'm going to pause and then just pull up Excel because I think you've seen everything you need to know about what to do in Stellarium. So now let's look at how to convert from DMS to decimal degrees in Excel. Remember in the slideshow, I told you how to take the number of minutes, divide by 60, take the number of seconds of arc, divide by 3600, and then add all that together. So rather than do that individually for every row, which is a huge pain, we just have to do it once. So you will have collected 3 columns of data when you're all done. That's the most labor-intensive part, is just collecting all the data. But it's still better than doing this with an actual telescope, right? At least you didn't have to get on a ship, pack a bunch of supplies, you know, your bacon and hopefully some citrus fruits. They didn't have toilet paper back then. It's just a rope hanging from the bow of the ship. Yeah, that's what I learned in 6th grade. And, you know, you're tolerating, not turbulence. What does a ship experience? Big waves crashing over the front of the ship. It's hard to sleep. You're crammed in there with a bunch of people, and then when you get to the island, there's no McDonald's there. There's no Disneyland. Of course, there's no Disneyland now either here in Anaheim. You've got to deal with flies and mosquitoes while you're looking through the telescope. Very often the weather's bad. Maybe the natives are hostile. I don't know. Or you don't know how to communicate with them. It's hard to find food. So don't complain about tapping some buttons on your laptop in Stellarium. This is super easy. Decimal degrees. Okay, equals. So when you hit equals, you're telling Excel that you're about to enter a formula. Equals, and then you click on the cell for the minutes, and each minute is a 60th of a degree. So you hit divide by 60. Plus, I had to do shift plus there, plus the number of seconds divided by 3600. What I'm doing is implementing the formula that I showed you in the slideshow. So it's this many 60ths of a degree, and F2, that's the number in cell F2, it's that many 3600ths of a degree. Once you've entered that formula, hit enter, and there it is. So Callisto was 0.1 decimal degrees to the left of the center of Jupiter, according to our angle measure tool. And then just like before, you can double click or click and drag, and it will repeat that calculation on all your data. So you only have to enter the formula once, and then you'll have one column of all your angular sizes in decimal degrees. Very convenient, much better than doing it by hand with the calculator. Okay, what's this all about? X in AU. Here's where we convert from angular size to actual physical distance. Just like converting from the number of degrees with the finger rule to the height of a door or the height of the Coca-Cola can, if that's what you used in the earlier lab. That's what we're doing here. This is where we need to multiply by, or take the distance to Jupiter, that's like r, and multiply by theta. This is really theta, right? We're talking about decimal degrees of an angle. So I didn't use the letter theta. Maybe I should have. I think I went with x to remember, or encourage you to remember that it's like a coordinate that can be positive or negative. But this is really my angular size in the field of view. This is the distance between Jupiter and Callisto in decimal degrees as seen by somebody looking at it, let's say through a telescope. Okay, so equals, and here's where I will implement the formula. First, I need that conversion factor. So in Excel, you type capital PI for pi. I don't think it actually has to be capitalized. And then you just put a set of parentheses with nothing in them. And Excel will recognize that that's supposed to be 3.14, 159, etc. That's pi. Divided by 180. That's my conversion factor. Now I multiply by the distance in AU. And then lastly, I multiply, and you'll notice I'm using an asterisk. That's shift number 8. Lastly, I multiply by my angular distance in decimal degrees. That's this column. So these two columns do not appear in the formula. You only use them to get the angular separation in degrees, decimal degrees. Hit enter. Okay. This is telling us that Callisto is 1/100th of an astronomical unit to the left of Jupiter. Does that make sense? 1/100th of an astronomical unit. Well, one astronomical unit is the distance from Earth to the Sun, and those moons of Jupiter are fairly close to Jupiter. I mean, they're not like, it's not just hop, skip, and a jump away. If you were in a car and you wanted to drive that distance, that should still take a long time. Driving to our moon would take a long time, and Jupiter's moons, I think, are even farther away. So this sounds reasonable, 1/100th of an astronomical unit. As we did previously, you can double click or click and drag to iterate that calculation. Okay? So the laborious part is getting all the data, and then you just have to enter some formulas and tell Excel to do what you say and repeat all those calculations for you. And you will have 28 days of data. You will know the distance to Jupiter, and more importantly, you will know how far Jupiter was, or how far Callisto was from Jupiter. And I think what I'll do now is pull up a spreadsheet where I've already done this, and I will be checking to see that your numbers are not simply my numbers. Right? You need to do this yourself, obviously. So you're going to have a screenshot here of my numbers, just so I can show you how to go about doing this. Okay, what I've done here is take my actual spreadsheet of data, and I took my legitimate numbers for the coordinates of Callisto and astronomical units, and I converted them all to a different column of numbers that is unrealistic. So your numbers are not going to come out like my numbers at all. This is just to demonstrate the process. I'm finding that for each of these coordinates, it's often 1/10 of an AU, which is too far. The Callisto is never that far from Jupiter. So again, these numbers are bogus. I'm just here to show you the process. The first thing we need to do is make a plot. Remember, we're going to read the period and the semi-major axis, or the size of the orbit, from the plot. So this is described in detail in the instructions. You need to read the instructions, but I will also demonstrate it here. I go to Insert. I'd like a scatter chart, and I think I need the one that connects the dots. Smooth lines and markers. It's been a while, but I think this is my best option. Okay. Now, unfortunately, Excel is making assumptions. It's making assumptions about which data I want to plot, which is really annoying, but you can get rid of that. So you right-click on one of the data points, go to Select Data, and see it's plotted all this garbage that I didn't tell it to plot. Remove, just get rid of all that. Okay, now the plot is empty. Good. Let's add a data series. Here's where we select which data we want to plot. So for series name, I can just go with X versus time. That's the coordinate of Callisto versus time. Now, don't be confused by this label. They're saying series X values. That is not our X values. Remember in high school algebra, anytime you looked, at a graph, the vertical axis was called the y-axis and the horizontal axis was called the x-axis. That's what they're talking about here. So this middle row really refers to the horizontal coordinate. If you think back to the slideshow, we want to plot position versus time. The horizontal coordinates are really the time values. So I go over here and click and drag on all my times in days. It's really just the numbers 1 through 28. And then they've got some syntax here representing that. If you hit Tab, you'll move to the next field, and you've entered that data. Now, I still don't know what this bracketed 1 is. Just delete that, backspace. And then they're calling it Y values. They really mean the vertical coordinate. And for us, that actually is X. The vertical axis is these coordinates that I'm calling X. So I need to click over here, all my distances in AU, and highlight all of them. And I like to hit tab again, just to make sure that it gets entered. Then you can hit OK. Then you hit OK again. So that's a really nice graph there. And it does indeed look like a sinusoid. And I immediately recognize I've got a peak here and a peak here. Remember when Callisto goes to the right, then to the left, then to the right? From this moment in time to this moment in time, that is when, or that's how long it takes for the motion to repeat once. That's the period of the orbit. Now, they don't have very many notches here on the horizontal axis, and you can fix that. And usually there's a plus sign here that you can use. I don't actually see that. So if I hover over one of the numbers, horizontal value axis, I'm going to right click, format axis. Aha. I need more units. So axis options, major. Let's try 1.0. See if that plops more numbers down. Hit tab. Okay, that's good. And then minor, they've got that too. You could even go with something smaller. Tick marks? Let's try tick marks. Minor type. Inside. What did that do? So I'm adding all of these to assist me in interpolating. Like I said, I encourage you to print this out. You can also probably do this in some piece of software on your computer. A lot of you guys are pretty tech savvy. You're turning in lab reports that are where you've typed onto the PDF directly, which is great. So you could do it that way. But if you were to print this out, you could draw your vertical line from the peak down. And to me, it looks like that's going to be around 3.2. See how this is divided into 5 subdivisions? So we've got 3.2, 3.4, 0.6, 0.8, and then 4. So to me, the peak looks like it's around 3.2 days. And then this peak over here is almost right on 20 days. So try to be as precise as possible. Use the extra tick marks. Again, I recommend printing it out. And then you just subtract the 2 days and you get your period. Now, remember, I made all this stuff up, but it looks to me like the period is... Okay, I'm just going to make up a number. I'm going to go with 15 days. I know that's not accurate, but again, I'm just trying to demonstrate the process. So I will go down here, and for the period, I'll put in 15 days, even though I know that's not correct. And for the amplitude of the orbit, well, if I hover over the peak, see how it's giving me coordinates? It says series x versus time 0.3. So it's actually giving me the coordinates of that particular point and then this particular point. The peak is somewhere just to the right of this point. And if I hover over that, and yeah, it's still giving me the coordinates of the 4th dot, not the coordinates of that point. So I don't think you want to write down those numbers. Now, the vertical coordinate, that's the second coordinate in parentheses. See how it says 4, 0.159? We want that second number, but it's really not that number that we want because that's the vertical coordinate for one of these dots. Now, this would actually be a good dot to use because it's right at the peak. And for that dot, the second number is 0.164. That would be a good value. I guess I'll keep 4 digits for now. 0.1643 would be a good value for the height there. Now, again, you could just print it out and then draw your horizontal line that intercepts over here. And let's see, if I hover over here, right click, format axis, let me make this smaller now. I'll change it from 0.05 to 0.01. See, now it just subdivided that axis. And I could even, under tick marks, I could add more of those. And now it'll be easier to tell that the peak happens at someplace between 0.16 and 0.17. So you figure out how to do that as best as you can. I'm going to go with 0.1643. So I'll go down here. That's the amplitude of the orbit, 0.1643. And that's it. I've got, well, not, that's not it, but we're mostly done. Now, your grade depends on what happens at the end here. If you don't finish the lab, you're going to get half credit or less. So you need to go all the way. The whole point here is to find the mass of Jupiter. That's what we're doing. I made these data up, so my numbers are going to come out all messed up. But the period of the moon in years. Okay, well, I just made up a number for the period in days, 15. Now we need to convert days into years. I did not demonstrate that in the PowerPoint, but think about it. What if the period was like 160 days? Isn't that roughly half a year, since a year is 365? So you would divide the number of days by the number of days in a year. So hit equals, click on the cell with the period in days, and then divide by the number of days in an Earth year, which is actually 365 and a quarter. That's the whole business with leap years. 1 year is actually defined closely as 365 and a quarter. Then you hit the enter button, and Excel has now converted the period from days into years. So how long, according to my made-up data, how long does it take Callisto to go around Jupiter? 0.04 years. That's hard to conceptualize in your head. You know, what is 4/100ths of a year? It's obviously less than a month, let's say. But now you've got it. So I will be looking to see that the numbers you plug in here are consistent with your graph. I need to see your graph. I need to see your data. I'm going to have the actual spreadsheet with your data in it, so I can check that you did this legitimately. Okay. For the mass of Jupiter, refer to the instructions. The formula is presented there, but it was also presented in the PowerPoint. Remember, m is a cubed over p squared. I solved Kepler's third law with Newton's update for the mass. So I can tell the computer to do this for me. So that would equal a cubed. A is the amplitude of the orbit in astronomical units. That's this number. And to cube it, I raise it to the third power. So that's shift 6. See that little caret symbol? That means raised to the, and then I enter the power, 3, and I divide that by the period squared. The period squared, well, that has to be in years squared. So make sure you're referring to the period in years. That's why I had to do this conversion, so that I'm dealing with the appropriate units. And I square that, and once I hit enter, I'm going to get the mass of Jupiter in solar masses. Now, how massive is Jupiter compared to the sun? Not very massive. Hopefully you know from your lecture that the sun is like, I think it's like 1,000 times as massive as everything else in the solar system. All the planets and asteroids, put all that together, the sun is still like 1,000 times as massive as that. So I'm expecting a very small number. Jupiter's mass in solar units should be a really small number. What? Okay, I think this is because I made up my data. Still, that seems suspiciously high. So let me make sure I didn't make a mistake here. Yeah, this result is ridiculous because of the way I tweaked the data. I produced some fake data here, so you couldn't just copy what I was doing. Of course, Jupiter is not 2.6 times the mass of the sun. It's got to be much less massive. So you're going to get a totally different number there. Lastly, if we want to convert, I showed you in PowerPoint, but we would just take, I'll hit equals, take the mass in solar masses, and then multiply by how many kilograms are in one solar mass, which I believe was 1.989 times 10 raised to the 30th power. And now they're giving us the answer in scientific notation. This E plus 30, that means times 10 to the 30th power. All right? So we're just about done here. One other thing I'm going to do is, it's a little overwhelming to have all these digits, and they're not meaningful anyway, because our measurements were only good to a few digits. So it's silly to keep all of these digits. So I'm going to click on these 3 cells, and there's a button right here we can use to decrease the number of significant digits shown. Oops. Okay. Doesn't seem to work for scientific notation, but this one. But let's show fewer digits, maybe 4 at the most. Same thing here. Don't chop them all off, because I need to see, again, I need to see that your numbers are consistent with each other. Now for percent error, that's how much your number for the mass of Jupiter differs from the accepted value. Now, I'm just going to make this up here. What's the easiest way to do this? Because we've got this pesky factor of times 10 to the 30th. Let's try this. Suppose yeah, I was looking for a way to avoid dealing with the powers of 10 here, but it really doesn't make a difference to Excel. It's not like we're doing this by hand. So here's what you do. Equals, open parentheses. You take your calculated mass of Jupiter in kilograms. So that just means click on that cell. That's a very big number, right? Times 10 to the 30th. And then you take the difference between that number and the accepted value. Now, I'm just going to make up an accepted value for the mass of Jupiter. Let's pretend it's 6.5 times 10 to the 30th. That is not the mass of Jupiter. I'm just making it up. So minus 6.5 times 10 to the 30th, close parentheses. That's the difference between the two. And then the whole idea of a percent error is to compare that difference to what you expect. We were hoping to get the actual, I'm pretending here, the actual mass of Jupiter, 6.5 times 10 to the 30th. You need to look up the actual mass of Jupiter and then divide that. So divide the difference by the mass of Jupiter, 6.5 times 10 to the 30th. So it's difference divided by accepted value. It's a ratio. To convert it into a percent, lastly, you would have to multiply by 100. So I'm off by almost 20%, and I'm on the low side. And I don't need to write the percent symbol here because it's already specified here. It's understood from this label that this is a percentage. So my calculated mass of Jupiter, according to made-up data, is on the low side by almost 20%. And then the last thing here, you want to compare Jupiter's mass to the Earth's mass. That's a fun question. How much more massive is Jupiter than Earth? Is it 500 times, 2 times? So you would just take the mass that you calculated, hit equals, click on the mass of Jupiter that you calculate in kilograms, and then divide by Earth's mass in kilograms. And you'll need to look that up. I'm going to open some parentheses. You would just put the number right there in the parentheses and use the appropriate syntax for the power of 10. Don't forget to hit enter, and I'll be looking at your whole spreadsheet. I'll be making sure that your data are consistent and that you got reasonable numbers at the end. They don't have to be perfect. There's no need to force the numbers to be perfect. If you did the procedure correctly, your numbers will be good enough. Okay, if your percent error for the mass of Jupiter comes out to be like 80%, you did something wrong. That's definitely too high. I'm not going to suggest an upper limit here, but I can tell you that 50%, that's definitely too big. See if you can get that percent error as low as possible. It's not going to be 0, so don't even attempt to do that. But you'll be surprised how accurate your determination of the mass is. So you will effectively weigh Jupiter. You're going to weigh the largest planet in our solar system by observing how quickly its moons orbit Jupiter and using Kepler's laws to process that information. And don't forget that you do need to read through the instructions. Not everything in the instructions was covered here in this video, so you will be responsible for reading those instructions. I need the spreadsheet. I need your chart. Ideally, you would print it out. If you do print it out and use a ruler to make those determinations of P and A, take a picture of that and include it in your submission, please. Thank you.